Hi and welcome everybody. My name is Krister Hammarling and I will present the thesis work Hydrogel-based pH sensors, development and characterization of optical and electrical pH sensors based on stimuli-responsive hydrogels. This is the outline of my thesis presentation. I will start with an introduction and background of this thesis work and present the motivation and research question. Then I will present the main findings of my work together with some theory, and lastly the conclusion and future work. The scope of the thesis can be divided into three parts. The synthesizing of a pH-sensitive hydrogel that has, to my knowledge, not been used in any sensor configurations before. These hydrogels have then been evaluated in optical and electrical sensor systems. I will also present a conceptual verification of a dual parameter optical sensor that can find particular use in many medical applications. So the introduction then. pH is measured in many different applications. In particular, it is used within many medical applications, for example, at intensive care units. Sensors in vivo is inside the body, should be small, so it can fit inside, be non-toxic, and be able to measure during long times, up to several days. In addition, multi-parameter sensing is very beneficial here, as you want to minimize the number of sensors. For example, many critically ill patients, it is important to continuously monitor the glucose level. But it's also important to monitor the pH level of the blood at the same time, as some of these glucose sensors are also susceptible to pH. Another example are complicated bone fractures. On a world basis, about 3,000 arms and legs are amputated due to complications beneath the plaster. And one way to measure this is, if there are any complications, is with a pressure sensor, like this one here. This is an optical pressure sensor that you can fit inside the arm or leg. Though this is not a fail-safe measuring method. One way to improve the probability to discover any complications is to measure the blood pH at the same time. Because then you can see if there are any lactic acid building up in the blood due to lack of oxygen in the muscles. So this optical pressure sensor here could actually be combined with an inline optical pH sensor into a dual sensor and measure these two parameters at one time. There are also many other areas where monitoring of pH is important. And fiber optic pH sensors are not always the best choice to utilize at that specific area. So sometimes you might need. Some of the areas I'm pointing out are, for example, wastewater treatment, industry processes within food industry, healthcare. I already mentioned in vivo, but there are a lot of other areas within healthcare you can use it, and concrete constructions. Concrete constructions, for example, suffers from pollution, air pollution such as CO2 and acid rain, which can lower the natural pH of concrete. And if the pH falls below 10, the steel reinforcements within the concrete will start to corrode, and this will eventually destroy the construction. So now over to the research questions and the problem motivation. To meet the diversity of the sensors that are required for many of these areas that I just talked about, some challenges has to be solved. New pH-sensitive materials are needed so that new and improved sensor designs can be developed. And as I also mentioned, there are also examples where you need to measure multi-parameters at the same time. From these research questions, I did a problem motivation like this. Considering the previously discussed areas where pH measurements are important, in this work I have studied new pH-sensitive materials and developed new sensor designs. This has resulted in new fiber optics as well as printed flexible pH sensors that can find future use in many of these areas. I have identified that pH-sensitive hydrogels is a good candidate to be used in optical and electrical pH sensor systems. And more specifically, I have identified a pH-sensitive hydrogel that is non-toxic, biocompatible, and suitable to be coated on both optical sensors and printed electronics. These hydrogels are then being characterized and evaluated in optical and electrical sensor systems. And I have also studied and evaluated a optical dual parameter sensor. So over to theory and results. The two most common ways to measure pH today are to use glass electrodes or pH paper sticks. Though there are also other techniques to measure pH. For example, ion-sensitive field effect transistors, ISFETs. ISFETs have started to replace the glass electrode due to that they are more robust and are easier to make smaller. We also have fluorescent pH sensors, and they are quite often used for monitoring bacterial growth samples and intracellular measurements, pH measurements. And we have, for example, imaging pH sensors that are quite often used in aquariums. I will now go into the main work of this thesis. A hydrogel is a subgroup of a polymer that has the ability to absorb water. And I have been studying the subgroup pH-sensitive hydrogels. The first hydrogel that was identified and investigated was based on a mix of 1,4-butane-diol deacrylate and piperazine. The synthesizing of this hydrogel was made without any solvents or additives by dissolving the piperazine in the butane-diol deacrylate. It is the piperazine that is the pH-sensitive molecule in this polymer chain. The hydrogel changes volume depending on the pH level. So in an acidic environment, the hydrogel protonates and expands by absorbing water. And in a basic environment, the hydrogel deprotonates, thus releasing the contained water. The absorbance or desorbance of water is a diffusion process, and thus it will take some time to reach a new equilibrium of the expansion. The change of water within the hydrogel alters the effective refractive index and the permittivity of the hydrogel. These two parameters are measurable by optical or electrical means, and thus can the expansion or the state of the hydrogel be correlated to a pH level. This is a 2D representation of a cationic hydrogel. Sorry. When the hydrogel starts to absorb water containing hydrogen ions, the ions will attach to the dependent group of the hydrogel. The large group will then start to repel from each other, and thus expanding the network and the mesh size, this one. And thus, it can contain more water. This degree of hydrogel expansion is governed by internal osmotic pressures, where the water absorption and the charge are acting as an expansive force, while the polymer network chains are acting as a resisting force. The hydrogel is a liquid, and then thus has to be transformed into a solid on the sensors. And this is done by adding a photo initiator and UV curate. The first sensor presented is a fiber optic amplitude sensor, meaning that it measures the change in optical output power as a function of the pH level. This is a simple technique that can be used in any wavelength from visible to near infrared, as shown here in the graph. The sensor was made from a multi-mode optical fiber, where a part of the fiber coating is stripped, and then the cladding was etched away with hydrochloric acid until the core was bare, and on that core I coated the hydrogel. During the characterization and evaluation of this first pH sensor, it was found that there is a large parameter space to consider. And we can divide this parameter space into two main groups. One that's about hydrogel and one that is more about the sensors. Some examples for the hydrogel parameters are adhesion. If you have a bad adhesion, the hydrogel will start to delaminate due to the physical forces from expanding. Viscosity. If the viscosity was difficult to make thin and even films. Wetting. If the wetting was not good enough, it started to build up droplets on the fiber before I had the chance to cure it. Some of the other ones are characterization, crystallization at room temperature, the amount of expansion with pH, and the curing of the hydrogel. Some of the sensor calculations are, well, I used flexible substrate, and that could be a problem with bending of the substrate due to the expansion force of the hydrogel layer. And that was especially noted for thicker films, of course. The pH responsivity, the length of the fiber, affects the responsivity. And the range, how far between which pH can I measure, that's strongly correlated to the hydrogel used and its expansion degree. Some other parameters are repeatability and optical fiber cleave angles and optical fiber lengths. During the evaluation of the first pH sensor concept, one of the observed issues was that the 1,4-butanediol diacrylate crystallized at room temperature. The crystallization at room temperature originates from the symmetrical structure of the polymer. To solve this problem, a new pH-sensitive hydrogel was synthesized, which is based on a mix of 1,3-butanediol diacrylate. This molecule has the exact same atoms and thus formula weight as the former one, though it is, as you can see, unsymmetrical. And thus it does not crystallize at room temperature. This hydrogel was synthesized in the exact same way as the former one. The pH-sensitive 1,3-butane hydrogel-based hydrogel proved to be pH-sensitive, as you can see in the graph to the left here, and it did not crystallize at room temperature. Though with a molar ratio of 2:1 between the diacrylate and the piperazine, I had problems with adhesion due to large expansion, and it was also challenging to make thin films because of high viscosity. Other molar ratios are possible to use, as for example 11:3 that has been used in Article 5. It could also be concluded that the UV curing need for the best performance to be done in inert atmosphere, which is shown here, where you can see that up here we are curing in inert atmosphere and down here in air atmosphere. This is especially important for thin films, since then the photoinitiator also needs to compete with the oxygen from air that is diffusing into the thin hydrogel layer. This improved hydrogel in Article 4 and 5. Now over to an electrical sensor, an electrical pH sensor. A pH sensor with capacitive readout is realized by utilizing the permittivity change within the hydrogel as a function of the pH level. And one way to make a sensor from an interdigital capacitance is like this. On a substrate, you first print an electric pattern, then you cover that with an electric insulation so that you don't get any shortcuts. And on top of that, the pH-sensitive hydrogel. Though it is very important to make the electrical protection layers as thin as possible, because if the electric penetration insulation is thicker than the penetration depth here of this sensor, the sensor will not work, since it doesn't reach out to the pH-sensitive layer. In this graph, 3 different pH sensors were measured. Remember that I said that it is a diffusion process to soak up water. And here I have 3 exact same sensors in size. The only difference is the thickness of the hydrogel layer, which is 10.5, 18.5, and 30.5 micrometer. And here we can clearly see that to reach stable point, the 10.5 micrometer thick film only needs about 6 minutes to reach the stable point, though the 30.5 micrometer films almost needs 30 minutes to reach a stable point. The stable point here is defined as where the capacitance deviates plus minus 1% from the last measured value in that series. And if we then look at the sensor that had 10.5 micrometer thick hydrogel layer, we can see the response here. And as you can see, it's sensitive to pH between at least 3 to 12. And I can say at least, since measurements above 12 was not conducted at all, and below 3 I had problem with adhesion due to the large expansion, and thus the sensor started to delaminate. It is also possible, very important, to consider the layer thickness, since a thin or a thick layer can give different sensor output. It can be seen here, where the red line here, that corresponds to a case A sensor, this one. And where you can see that the hydrogel layer is thinner than the penetration depth. So the penetration depth also can sense the surrounding area, the blue here. While the blue one is a case B sensor. There the hydrogel layer is so thick that the penetration depth doesn't reach outside the hydrogel. And as you can see, we have the opposite responses of these two sensors. In the first one, when we go from a low pH to a higher, the capacitance increases. While in case B, the capacitance decreases. This behavior is easiest explained with a simulation. This is a simplified simulation of these cases. For case A, when the hydrogel expands, the capacitance will decrease, and that's the blue top line there. This because pure water has higher permittivity than the water-soaked hydrogel. So when the water part here decreases due to expansion, it pushes away the water, the total capacitance will decrease. While for the case B sensor, when everything was within the hydrogel, the more water it contains, the more swollen it is, the more capacitance that sensor will have. Then you can also see we have a case C sensor. And that is actually a case A sensor in the beginning. As you can see, it declines. And then as the hydrogel gets thicker and thicker, it eventually will become a case B sensor. So over here, it is a case B sensor. This is not optimal, since you really don't know the behavior of the sensor. These theories that I now have talked about for the electrical sensor is also applicable for any optical sensors that are utilizing a sensing field. So let's have a look at one type of fiber optic pH sensor. This sensor is based on a Mach-Zehnder interferometric technique. This one here. Manufacturing of the sensor is made by splicing a piece, up to a few centimeters, of thin core fiber between two single mode fibers. And then the hydrogel layer was dip coated and cured on top of the sensor. The bottom left graph here, you can see a typical output spectrum from this kind of sensor, where I have pointed out two distinct minimas. The number of minimas and positions of the minimas depends on the length of this sensor. In the middle picture here, on bottom, there is two pictures from a simulation where I show the input part here, it's the top, and the output part here. And as you can see in the output part, that only certain modes will recouple into the output fiber, the middle one here. All the rest will be lost. And on the right, it's a schematic principle of the measurement setups I used for all the optical measurements. Here we can see a graph that shows the pH response from a Mach-Zehnder interferometric pH sensor. In the main graph here, you have points. These points are taken out from the minimas of the spectrum. And here we have samples of these minimas. The error bars are computed from the optical spectrum resolution of the optical spectrum analyzer. I have some computational errors and also consecutive measurements errors. So these are the error bars here. Though, as you see, some measured output values can correspond to two different pH values. As for example, both pH 2 and pH 8 give the same output value of around 1,703 nanometers. To explain this, you first need to know the principle of the sensor. Inside the fiber, there are total internal reflection, though a part of the light's energy reaches outside. This is the reaches outside the fiber, and that is called an evanescent wave. And if the energy of this part is somewhat altered, also the light inside the fiber will be altered. Also, this evanescent wave has a penetration depth, as you can see here. So, to explain this behavior, at low pH, the hydrogel is thick. Thus, this sensor behaves like a KSB sensor. The hydrogel is thicker than an evanescent wave. While at high pH, the hydrogel is compressed or shrinked. And thus, it is below the evanescent wave, and the evanescent wave can sense the surrounding. Altogether, this is a case C sensor that can be both the type A or type B sensor. This is not an optimal sensor layout, as you can see for some values you get one output for two different measured values. Remember that I said that the absorption and desorption of water takes time. Despite that, it is possible to make fast sensors, as shown in this graph. Here I have cycled an optical pH sensor between pH 7.1 and 8.15. The sensor response is faster than 15 seconds. How fast I cannot tell you exactly, because the optical spectrum analyzer in this experiment could not measure any faster. Now let's have a look at the dual parameter sensor. This is how a conceptual dual parameter sensor could be built. It consists of a Mach-Zehnder interferometer here and a Fabry-Perot interferometer here, the green one. And for example, the Mach-Zehnder could measure pH and the Fabry-Perot glucose. The output spectrums from the Mach-Zehnder, as I showed before, looks like this. This is a low frequency spectrum. And for the Fabry-Perot, it will have a high frequency spectrum. And since the two sensors have different frequencies, it is possible to separate them with high or low pass filters. In this experiment, I have taken the principle of this sensor and measured the solution's refractive index with the Mach-Zehnder interferometer part and the ethanol concentration of the same solution with the Fabry-Perot. And as you can see in the left graph here, where I have changed the refractive index, the ethanol concentration seems to be quite stable, so I have a small crosstalk. And in this graph, I have done the opposite. I have changed the ethanol concentrations while I had held the refractive index constant. And also here, we can see it's only a small crosstalk. So to the conclusions. The investigated hydrogel are very promising for pH sensing applications, as they respond to pH in a wide range. The hydrogels are also suitable to be used in both optical and electrical sensor configurations, since they change both the refractive index and the permittivity in regard to pH, and that they are coatable on multiple substrates, such as glass and plastics. The conceptual dual parameters show small crosstalk between the two sensors, and is thus a promising technique to build on. As for future work, I would like to say some words also. I would like to characterize the hydrogel regarding other ions and ion strength susceptibility, and also UV resistance and long-term stability. The optical Mach-Zehnder interferometer should be redesigned so that it works in the telecommunication bands instead, where there are cheaper hardware and have the possibility to use, for example, amplified spontaneous emissions light sources and dense wavelength division multiplexing readout systems. The adhesion problem should be further investigated by, for example, experimenting with different primers and plasma treatments. And lastly, I would like to further investigate and develop the dual parameter optical sensor. Thank you.